Good afternoon and welcome to session 2 of the AI and Autonomy track. It is my pleasure to introduce Dr. Carlo Lipizzi from Stevens Institute of Technology. Dr. Lipizzi is a machine learning and data science professional serving both academia and the private sector. As a member of the CERC, Dr. Lipizzi has served as a principal investigator on multiple research projects with the convergent use of natural language processing, machine learning, data mining, and data visualization. Today, Dr. Lipizzi will be presenting updates on his research task, WRT-1023, analyzing and assessing contracts for embedded risk. With that, I turn it over to you, Dr. Lipizzi.
Thank you, Cara. Thank you all for joining us this afternoon. Beautiful day outside. My name is Carlo Lipizzi. As Cara was mentioning, working at the Stevens Institute of Technology and CERC, primarily focusing on AI machine learning and in particular on natural language processing. So those are the main focuses or foci on my research. Within the activities on NLP, we started working with DAU on analyzing the contracting universe, and in particular with determining if we could be of any help working with the contracting officers to give them a point of reference, let's say, in their job. No intention of replacing any of the steps of the contracting in a broad sense, but with the idea of defining a knowledge-driven approach that can be of support of the process of classifying requests by contract type. So we used an approach that is heavily relying on natural language processing, and in particular on recreating or creating a computational version of the knowledge of a contracting officer. So that's the idea. The project was distributed in several phases, and the goal was to deliver a proof of concept that it didn't want to be a product because the duration was too short, but just a way to see if the overall idea could work, and eventually if that idea could be applied to similar cases. So some of the key features. So we wanted to leverage on the modus operandi and the literature within contracting in a broad sense. We wanted to create a logical framework to classify requests based on given contract types. We want to create a computational model for this representation and eventually add some visualizations of the results and present the results in a way that was somehow usable without going in crazy terminal mode or things like that, because the system was developed in a computing language that was Python, but obviously the users will need a user interface. We focus on 10 different contract types, some with several degrees of similarity, some others completely different, but the way a contracting officer is discriminating one from the other is far from being black and white. So the issue was to create a classifier that was based on, let's say, principles and not common practice. Because if the classification was not done in the proper way, probably we would reiterate the same approach. So the idea is to define somehow the rules of the game, in a sense, apply those rules of the game to the way a generic, a theoretical contracting officer could act, and propose some classification for the documents that we received. So the approach, the classification was rooted into semantic analysis of text. Analyzing semantic in text is far from being an easy task. It's a complex task with so many gray areas, and overall there is no perfect solution for a human level semantic analysis. So when we talk about text understanding, text labeling, those are tasks that are human, and there is no automatic solution inside that can really provide the same approach. But between having a machine acting as a human and having no support, there is quite a lot of room to introduce solutions that can be helpful. Generally speaking, it's a number game, meaning if you have one single document that you want to analyze, and is one document each year or whatever, you probably can do it manually. If you are analyzing on the extreme messages from social media by the billion, you cannot do manually. So if you can get a semantic analyzer that automatically will make your life easier, that's what we want. So the idea was to analyze things from the point of view of a contracting officer. So this concept of point of view is really essential in the overall approach that we are having in NLP. If I read something, this something, the interpretation that I get of that something will most likely be different from the interpretation that someone else can have. The example that I use the most in those cases is about emotions. So there is a classification of emotion. Based on that classification, ecstasy is a shade of joy. If you are reading a text and you are a psychologist, then when you read ecstasy, you think about a shade of joy. If you are anti-narcotic, then you read ecstasy as a drug. If you are into religions, then ecstasy is a step toward the divinity. So it's the same word with completely different meanings, depending on who is reading it. So when we approach text, there are three biases. The bias from the source, so the one who wrote or generated the text, the one who is reading the text, and the one who is creating the model for understanding. So the creating the model is what we are doing, is the system doing that job. The other two portions, we cannot do anything on the source because that's what we have. But we can define who is the reader and how the reader would interpret the same text. So that's what is behind the first line saying rooted in a semantic analysis of text. So we want the third bullet to recreate the contracting officer knowledge and use that for the classification. we reused an approach that we developed for another WRT for the DoD. That is a framework of representation of knowledge. So this piece is something that I call the room theory, and is based on the framework theory by Marvin Minsky. Marvin Minsky used as an example, when you enter a room, you know right away if it's a bedroom, a bathroom, or something else. Not because there is a label, but because what you see is kind of resonating with a framework of rooms that you have in your mind. And obviously, if someone else is entering one room, may have a different interpretation. Probably not for all of them, but for some of them. So those are framework based on a previous theory, the schema theory, basically with the same overall approach. In that period, I started working in AI in '86, between mid-'70s when the theory was created and mid-'80s. There was not much in terms of computational options. The hardware we had was not very powerful. We didn't have Python or something like that to create models and to make them effective. So I introduced a computational step, vectorizing the corpus representing the knowledge and creating a matrix that is called embeddings. There is a table with all the unique words and a set of numbers defining in that particular text the word, creating a computational representation of a corpus. If the corpus is representing the knowledge in one domain, the embeddings is basically a computational representation of a knowledge. So then putting pieces together, you have a room that is this computational version of the knowledge of a contracting officer. You have the requests that you want to evaluate, and you have the elements you want to target, meaning the elements in this case that are distinctive characteristics of the different contract types. So you basically take elements that are words or combination of words from 2 and 3, meaning the requests and the benchmark. You compare them doing a lookup in the room, meaning you have the words, you go to the room, that is a table, and you look up the word and get the vector, meaning the n numbers defining the word. And then you compare those two vectors, and by comparing them, you will determine how far they are. And then you iterate along all the words or the semantic elements in the requests, all the words in the benchmark, and then at the very end, you will have one contract type with more similarity than the others to the request that you are analyzing. So that's the overall approach. If you change the room, you will get different results, meaning the room, it's basically where you are going to get those vectors. So the same word will have different vectors with different rooms. That's basically what is happening when I read ecstasy, when the anti-narcotics is reading ecstasy. So different knowledge base provide different interpretation. So we started with a knowledge base that was based on the contracts only, with the keywords defining the contract types that were about 100, meaning about 10 each contract type. So we had about 100 keywords defining the benchmark. So we are right here, the benchmarks. We have about 200 documents, 30,000 unique word for the room, for the knowledge base. The results were not great because sometimes the lookup of the words returned empty because there was no word in the table, because the 30,000 unique words may have been not enough. So I went back to the sponsor. I asked, how do you hire a contracting officer? What are the types of education they need? And the idea was some MBA-like, some law school-like. So we expanded the corpus that we used to generate the knowledge base, including the education for those two areas, and expanding overall the corpus, and therefore the computational representation of it. We expanded the keywords, including combination of words, including misspelling, getting 464 keywords, 537 documents, 120,000 unique words. So at that point, the base was more reasonable. It's not representing, obviously, entirely the knowledge of a contracting officer. This was a proof of concept, and it was anyway a subset and always will be. Another key issue was to develop the combination of words that we call engrams. System engineering is a bigram, is an engram. School of business is an engram, is a trigram. So we want to extract those engrams in the same way across the three components of the system. We also added weights to the keywords, because not all the keywords in the benchmark are so defining for the contract type. And then we changed the way we calculate the distance between those two vectorized words, and we created a little bit of a user interface. So that's basically a comparison between the previous and the current approach with the different, with the changes in the previous slide. And it's basically comparing by different contract types, the different results. But this is probably more evident here. This representation is called principal component analysis, and it's basically, the words, they have 300 components, meaning they are in a space with 300 dimensions. PCA, in this case, has two dimensions, meaning it's not a representation of what we have, but it's kind of projecting the 300 dimension in two, and is giving a sort of an idea. So the one on the left is basically how the system was able to differentiate one contract type from the other initially. So the differentiation was not great. If you see the area in the middle is kind of overlapping a lot. With the new system, meaning with a bigger knowledge base, with better keywords, different algorithms, weights for the keywords, the differentiation is definitely better. Then obviously there are proximities. In a fixed price there are three different types, and they are different, but they're not that different. So that's basically the result that you see on the right side. On the left side, you have the different types of contract. So you have two main types, but then you have a total of about 10 subtypes. So on the right side, you have a table where you basically have the different requests, and you have the contract types, and you have the percentage of accuracy if you use that contract type to classify that request. And then the last column is basically telling you what is the winner. So what is the value that is highest in the bunch. And in this case, the first one is 43.17%. So the system is telling that based on what we have, the most appropriate contract type for this request is FFP. And then obviously different requests will be with different contract types. You also, you as a contracting officer, may also see the other that are kind of close and say, okay, the system is telling me that, but it's also saying, like in this case, you have one value that is bigger than the other, but not by much. So this 25.53, 29.06, and you have 25.20. So the contracting officer can also go through the other two types and say, okay, the first one is the winner, but probably I may want to consider other. So we ran a little bit of a simulation to see, how separated were the elements and how good the classification was. We applied it to two different use cases, individual documents. Sometimes you have one request that is defining 100% of the request itself, the logical request. Some other times you have documents that are concatenated, but basically they are related to the same request. So those are the two different approaches. Let me go for a second to the system that should be here. Here we go. Sorry about that. So that's the user interface. So the user interface is plain and simple. We didn't want to create any distraction. So you basically can either drop or click and get, let's say I want two of them, those two, and then I upload them, then I submit. So now the system is running in background, generating the report that I was mentioning to you. So the system is relatively computational intensive because at the very end you have a relatively large matrix and you need to do all the comparison. With the new algorithm, we are faster, but considering those are only two documents, is taking a lot. So the next phase, we will improve the performance. We have some ideas, but that's not the moment to review it. So basically, you have, just as in the slide, you have the two files, the two requests, you have the different contract type, and you have, as last column, the one who is the winner, meaning the one with the highest value. Similar thing for the second one. And then you can see a little bit of visualization that will show you how separated are the different contract types for those two requests. So this is basically the user interface that I was mentioning before. let me go back to the slides. So the current system is a proof of concept, and we know that it's not tested on a larger scale. We know that it's going to be slow if you have a lot of documents. We know all of that. It may crash at a certain point. I mean, it's a proof of concept. It's not stable to be a product. It's not supposed to be. We want to introduce a sort of after triage supervised system. So the more I'm working in natural language processing, the more I'm leaning toward a system that is more combination of an approach like the one that I'm using here, that is basically primarily unsupervised, with an approach that is more supervised, more traditional, rule-based, or symbolic, as is normally called. And we are working on another project for DAU that is following exactly this approach. So the idea is to combine somehow using our system as a sort of triage system, but then introducing a sort of rule-based super system that is taking the input and applying the rules and filter out the results. We want to expand the user interface, and we are transforming the tool in a learning tool that can be used by younger contracting officers as a way to evaluate, compare their choices. Working with natural language processing is a process itself. So again, there is no existing solution, even the super expensive, super sophisticated, that are really addressing the concept of understanding. So processing is something, understanding, it's an entirely different game. Understanding is for humans. We are, so the most sophisticated approach that we have now in NLP are based on a model that is called transformers that evolved and is rooted in neural networks, in what is called deep learning, meaning you have a neural network as an input layer when you provide the input, and an output layer with the results. In the middle, you have what is called the hidden layers, layers, where you have the elaboration of the input to get the output. Those systems, those deep learning, may have millions of hidden layers, meaning they are so complex that there is no way that you can check what's going on. Based on that and the approach of the transformers, OpenAI developed GP3, that is a supervised model based on deep learning with 175 billion parameters. So those parameters are basically weights that you give to the input. But it's what it is. It's so big that cannot run on your computer, but you need to write an API and get the results. So, but basically, this is modeling the brain, not the mind, meaning there is no way that you can really understand the text. Understanding is for human beings. So we do not have a model for understanding. So we are just speeding up a process, considering it a black box, but that's not the way the mind is working. So using this approach and kind of leveraging on the room theory that seems to be somehow a way to represent the knowledge, probably not the best, for sure can be perfected in the line of epistemology, the study of knowledge. We are working on two projects. One is matching projects with funds availability. So in this case, we have individual projects that are requests eventually, and we have funds opportunities. We clean and engramming the sources. We get the vectorized documents, and then we do the matching. So with an approach that is pretty much similar to what I did for the contracts. The part on top is basically filtering out the results, considering the point of view. So same thing, a corpus that will become the knowledge base, the room, and the benchmarks indicating the points of those, the benchmarks and the matching elements will be filtered using the point of view in the corpus, in the room. And then you will have a ranking, and you have the pairs, projects, funds that will match the most. Another approach, and this is my final slide, is on extracting causal chains from text. Causal chain in some domains are called kill chain, and is basically the functional hierarchical relationship that we have in objects that can be in an attack. So we have a weapon and we want to go down in the hierarchical chain, attack the element that is maximizing the result and minimizing the side effects. Or can be in marketing. You have cellular phones. Cellular phones, they have technologies that are concurrent to the cellular phones. That can be batteries, screens, antennas. So you want to recreate this chain, this causal chain, because that can lead to a better strategy on the field, or can be something that you can use in your marketing strategy. Same thing, the flow on top is basically providing the point of view that can be the marketing or the defense. The benchmarks are the elements of attention that you want to consider as a driver for the selection. And then the flow at the bottom is basically just taking the documents that you want to analyze. You generate the matrix. From the matrix, you generate a network that is representing the elements in this matrix. There are several ways, but basically you calculate the similarity between the vectors, and the vectors that are more similar than a threshold that you defined, they are connected. So that's the semantic network. From that, you generate clusters. And then from the clusters, applying metrics in network analysis, you recreate the causal network. So that's basically it. I really hope that this presentation was interesting and useful for you. And saying that, I will stop sharing and ask Cara to take it over.
Thanks, Carlo. Thank you so much. If we have any questions, please enter them into the chat here. I don't see any at this time, but you are just at time, Carlo. So we're going to set up for Azad right now. If there's any questions or comments, you can follow up directly with Carlo through the platform. Thanks, Carlo. Thank you so much.
Thank you.